Okay, in this video we're going to look at slack variables and duality in the simplex algorithm once more, and students are advised to go back and look at the video that I created regarding row matrix operations. Those would be helpful in this. So recall our problem with wheat and corn output. All right, recall that revenue was 3x1, where x1 is wheat measured in tons, plus 5 times x2, where x2 is corn measured in tons. We had a land constraint where 2 units of land were required to produce a ton of wheat, and 4 units to produce a ton of corn. And we only had 16 units of land, and we had 18 units of labor. 6 units of labor were required to produce wheat, and 3 for corn, and we have this non-negativity constraint. So we set up the what's called the initial primal tableau. You'll notice here that we have column Z. The first row refers to the first constraint. We had 2x1 plus 4x2 plus the slack was equal to 16, so it had to be less than or equal to 16. Notice that the slack here enters the bases and is equal to 16. The second column, or second row, we had 0 value for Z, 6x1 plus 3x2 plus 1 slack variable gave us 18. And down here we just have this 1 indicating that we have 1z is equal to, when we subtract the x1 and x2 in the objective function, we get minus 3, x1 minus 5x2. So just familiarize yourself with the setup of this tableau, and if need be, compare it to this setup here, the LP that we have. All right, so we begin this by looking at step 1, entry. Choose the most negative value in the bottom row for entry. So in this case, x2 enters. So now we have to determine the second step, the minimum ratio criterion. And we look at 16 divided by 4, which gives us 4, and 18 divided by 3, which gives us 6. We have to take the minimum of that. So when we do that, we can enter 4x2, and we get, we enter 4x2, but we get rid of the x surplus value 1. All right, so we get rid of the surplus variable associated with the land constraint. So the pivot element is circled, and it must be positive. If it's negative, then we cannot choose it. So the pivot element must be positive, as must all the elements in the shaded column above the bottom row. All right, so then we use row operations to get the new or next tableau. So the initial tableau, which is this one here, needs to be changed, and we do this by multiplying the first row by 1/4 to get 1 in the column under x2. So we get 1/2, so 2 divided by 4 is 1/2, 4 divided by 4 is 1, 1 divided by 4 is 1/4, and 16 divided by 4 is 4. So this indicates that where the 1 is, that's equal to 4. So x2 is equal to 4. Now, one thing to note before we go on, notice that this is a identity matrix. And once we solve this thing, if this was an identity matrix here, so this is our original matrix, if this is an identity matrix and these were 2 equations and 2 unknowns, then if we can shift through row operations this identity matrix over to here, then the solution would appear in this matrix here in terms of the inverse of that matrix. All right, so getting back to the row operation we use, we first get rid of the first row, or change the first row by dividing by 1/4. Then we now use row operations so that the remaining entries in the x2 column are 0. So we take the new second row and it's equal to the old second row minus 3 times the new first row. So we take that first row and we subtract 3 times it from the old second row, and that gives us 9/2. This becomes, or this was a 0. Pardon me, this becomes a 0. All right, and if you recall, we had that 3 in here, so that's why we subtract 3 from 3 times the first row from the old second row. We had a 3 in here, we had to get rid of it, and as a result, we change all of these numbers going along. So we get a 6 here. Then we take the new third row is the old third row plus 5 times the new first row, and that gives us a 0 in here, and it gives us these numbers over here. So the next step is to look for the negative value in these two columns, and if there's no negative value, we're done. But there is a negative value here, so we choose the most negative value in the bottom row for entry, so x1 enters. So x1 has to go in. So we use the minimum ratio criteria, so 4 divided by 1/2 gives us 8, and 6 divided by, so 6 divided by 9/2 gives us 4/3. 4/3 is the minimum, it's less than 8, so XS2 has to be removed. We do that in the next slide. So the second tableau that now needs to be changed is this one. Okay, that was just a repeat of the tableau on the previous slide. So we multiply the second row by 2/9 to get 1 in the column under x1. So we multiply by 2/9 here, 2/9. This multiplied by 2/9 is 1/6 minus 1/6. 2/9 times 1 is 2/9, and 6 times 2/9 is 4/3. So now we got to change the other rows appropriately. So we use row operations so that the remaining entrants in that x2 column go to 0. So we take the new first row, and it is equal to the old first row, this is the old one, minus 1/2 times the new second one. This is the new second one here, and this remains a 1. This becomes 1/3, 1/9, and 4 minus 1/2 sixth is 10/3. So this becomes the second row, which we had before. So we had the third, pardon me. So let's go back to the first row a minute. The old first row, this one, minus 1/2 the second row, the new second row. So this is the new second row. So this is 1/2 would be 4/6. 6 minus 4/6 is equal to 10/3. Same thing with the new third row. It's the old third row plus 1/2 times the new one. So if we add 1/2, this becomes a 0. 5/4 plus 1/2 of this is, because we're dealing with the new one, we get a 0 there, or pardon me, we already had a 0 there. We got the old third row, 5/4 plus 1/2 times 1/6 is minus 1/6 is gives us 7/6. We get 1/9 and we get 20 and 2/3. So notice that we've gone up from 20 to 20 and 2/3 when we introduced this, when we shifted land in corn into wheat to pick up that slack labor that we had. So note that in the final solution, all the entries in the final or the objective function row are positive. So the entry requirement says no variable will enter the basic feasible solution because there's no negative here. So these are the 4 variables that we could have into the new solution, but there's none that is negative, so then this is the final solution. The dual variables are the shadow prices. These are the shadow prices. So in other words, if we had one more unit of land, we'd increase the objective function by 7/6. If we had one more unit of labor, we'd increase it by 1/9. So the dual variables are the shadow prices, y1 and y2. The dual slack variables are ys1, ys2, and they're both equal to 0. So the solution is y1 equals 7/6, y2 is 1/9. The primal slack variables are also equal to 0. And the solution is that x2 is 10/3, x1 is 4/3, and z is 20 2/3. So the optimal solution is found. An unbounded solution. Wonder if we get that. The value of the primal objective increases without bounds, and it occurs when it's not possible to find a pivot element in the entering column because all elements are less than or equal to 0. So that's an unbounded solution. Infeasibility of one or more constraints can occur when constraints are inconsistent and there's no feasible solution to the problem. This is a frequent result in linear programming. Degeneracy can occur if there are redundant constraints. So for example, x1 has to be less than or equal to 25, x2 has to be less than or equal to 25, and then if you have an additional constraint, x1 plus x2 less than or equal to 50, this constraint is totally redundant. More than one optimal solution is sometimes possible. A variable is brought into the basis without increasing the objective value, and that can occur when the objective, the line for the objective function lies on top of one of the constraints. So anything along that from the two vertices in that constraint can enter the objective function. Now we also have what is called the dual interpretation, and we'll get into dual variables or duality in more detail in the next set of lectures. The marginal rate of technical transformation from x2 to xs1 is 1/3, and that's right here. This is the 1/3. And the marginal rate of technical transformation of x2 to xs2, the slack variable, is 2/9. That's 1/9. x2 to, let's see, x2, here, that's 1/9. x1 to xs1, it's minus 1/6, and x1 to xs2 is 2/9. There we go. The opportunity cost of land is equal to the sacrifice in terms of corn and wheat minus the unit revenue of land. You've seen this equation in the previous lecture, and it's equal to the unit revenue of foregone activities times the marginal rates of technical transformation. So this is the 5 and 3 were the objectives, 1/3 and minus 1/6, 1/3 minus 1/6. Those are the marginal rates of technical transformation. And we get equal 5/3 minus 3/6 when we multiply these two vectors together, and we get 7/6. So this is the land slack variable. The opportunity cost of labor is the same objective values, but now we got minus 1/9, and we have 2/9 as marginal rates of technical transformation, and when we multiply these two vectors together, we get 1/9. So that's the opportunity cost of labor. So we have the opportunity cost of land is 7/6. The opportunity cost of labor is 1/9. All right. So we have 1/6 and 7/6. Pardon me. There's your opportunity cost of land, and here's your opportunity cost of labor. All right, the opportunity costs, also known as the imputed marginal values, sometimes known as the dual variables, or even the shadow prices. So we go back up here, these are your shadow prices, and they're equal to the value of marginal product. So we have the value of the marginal product is equal to the marginal revenue times physical marginal product, and if we don't have perfect competition, if we have marginal revenue. If we have perfect competition, this is just price times marginal product, which is the value of the marginal product as well. The original problems, the primal was maximize profit, 3x1 plus 5x2, where we have wheat and corn, 2x1 plus 4x2 less than or equal to 16, 6x1 plus 3x2 less than or equal to 18, non-negativity constraint, and we can create the dual, we can find the dual, which is 16y1 plus 18y2, 2y1 plus 6y2 is less than or equal to, greater than or equal to 3, and 4y1 plus 3y2 is greater than or equal to 5. And the dual variables y1 and y2 are greater than or equal to 0. Okay, and these are the solutions x1 and x2, pardon me, because of the 1 here, and 4/3 because of the 1 there. Okay, so if we look at that primal or that basic setup, then we have the primal variables here, the primal slack variables here. These are the marginal rates of transformation of x1 for x1 all the way across to marginal rate of transformation 1 for n, and so on down. So we have m constraints and n variables, and these are all your marginal rates of transformation in this matrix here. This matrix here contains your marginal rates of technical transformation from x1 to the slack for 1 all the way across to marginal rate of technical transformation of x1 for the slack, of x1 for the slack in equation m. Here it's marginal rate of transformation of the m equation with regards to slack 1 and m equation with regards to slack n. And this should be an n, not an m. Then we have down here our c values, which were the values up in the original constraint here, 3 and 5, but we use a negative value because z, we had z here before, and that z is positive. We subtract the x1, 3x1 and 5x2 from it, and that gives us that. We get these slack ones here, and these are our solutions across the bottom here for the dual slack variables and the dual variables. So these are the dual slack variables here and the dual variables here. This is the solution to z, the objective function, although we had it down here. This is the solution to the, pardon me, these are just the labels. This is just a label across the row. And the actual value of the profit is given here. The solutions are given here, and the x's, wherever there's 1 in this row, is given by the solution here for the basic variable. That's the basic one there. And you'll notice here that you have a problem if m and n differ significantly. All right, so return to the initial primal tableau, and you'll see that you have these results here. And we can write that in this way here, where this a, I, j star is given by 2, 4, 6, 3, and the, it's given by this entire component here. These are your minus c's. The value of z is here, and the xbi's are here. The dual, as we've written it, looks like that, and we can also multiply it by minus 1 on each side to get it into the standard format, where minus r is equal to minus 16y1 minus 18y2, minus 2y1 minus 6y2 is less than or equal to minus 3, minus 4y1 minus 3y2 less than or equal to minus 5. We still have the non-negativity conditions, and we end up creating this tableau. All right, this tableau is a little bit different because we have the minuses here, and we have here is the zj minus cj. So the thing is kind of flipped. But we now have to look at cases where it's not possible to solve the primal problem, but by going to the dual, it's possible to solve the problem using the dual simplex algorithm. So you see, this setup is just a flip, like the former primal problem. So what do? Well, we now, in the primal problem, we looked at what minus cj was the most negative, and we looked at that, and that would be the one to enter. And in the second step, we took the minimum ratio. As long as they were positive, that would be the exit criteria. Well, with the dual algorithm, it's not surprising. The first step is to choose the most negative xbi here to enter. And then step The second step is to choose the minimum value of that ratio as the exit criterion. So it basically is the same, except we're working across now in this direction first and then that direction. Before it was this direction and then that direction. So you can see, if you think about it, the primal algorithm and the dual simplex algorithm are very similar in many ways. So the point is, if you end up with a situation like this, you'll notice that the primal algorithm doesn't work because there's no negative value here. They're up here. So what happens is you basically start here instead of down here, and you try and solve the problem. So how does this work when the values in the bottom row are all non-negative? Well, because all the minus Cj are greater than 0, we have a dual feasible solution. So we begin under solution by choosing the most negative value, which is minus 5, and use the minimum ratio criterion for determining what y to enter. So 18 divided by minus 3, so that's it's a minus 3. 16 minus 4 is 4. So that tells us that this one goes in. This is our pivot element, and again we do the same thing. So we compare the dual simplex algorithm on the previous slide with the original tableau and approach used by the simplex algorithm below. This is what we did below, and here the pivot element must be positive, but in the dual algorithm it must be negative, as shown up here. All right, so it's the negative value here, and remember we're doing 18 divided by minus and then a minus 3 and a minus 4. So that's the big difference there. So the primal Lagrangian would look like this: 3x1 plus 5x2 plus y1. y1, remember, is acting as that lambda 1. 16 minus 2x1 minus 4x2 plus y2, which is our lambda 2. 18 minus 6x1 minus 3x2. The dual Lagrangian looks like this. It's 16y1 plus 18y2 plus x1. Now x1 is acting as the lambda 1 and x2 is the lambda 2. And by solving this through, we can show that this dual Lagrangian looks exactly the same as the primal Lagrangian. So the dual and the primal are bound together by a common Lagrangian. If we look at the dual primal solutions, if the solution to the primal is unique, non-degenerate, and optimal, the optimal solution to the dual is unique as well. When primal has degenerate solution, the dual has multiple optimal solutions. So if the primal degenerates, the dual has more than one solution. That's optimal. When the primal has multiple optimal solutions, the optimal dual solution is degenerate. When the primal problem is unbounded, the dual is infeasible. And when the primal is infeasible, the dual is either unbounded or infeasible. So let's look at the Karsh, that should be Karush, K-A-R-U-S, Kuhn-Tucker conditions and linear programming. All right, so here we have our traditional setup: z equals c of x, a of x less than or equal to b, x's are positive. The Lagrangian is c prime of x. The prime just means transpose. Y is transpose b minus ax. First derivatives look like this: c minus y prime a equals 0. b minus a of x, which is just this back, is equal to 0. Here's the dimensions of the various vectors and matrices. C is an n by 1 vector, x an n by 1, b an m by 1. And because it is an n by 1, we need to take the C transpose in order to make it a column vector. A is m by n, x then is a row vector, a prime is n by m as opposed to m by n. And the dual problem is minimize r y of x. A transpose y transpose is greater than or equal to c. Y is greater than or equal to 0. C is, remember this one up here. Here it's a column vector. There it was a row vector that had to be transposed. The Lagrangian is yb plus x prime x transpose, all multiplied by this inside here is c minus a transpose y transpose. First derivatives of the Lagrangian with respect to y gives you b minus ax 0. That's exactly the same as here. and dl dx, the partial of L with respect to x, c prime minus y prime a 0, and that gives you the same thing as here. So these primal and duals are tied together, but the KKT conditions require that c prime minus y prime a is less than or equal to 0, c prime minus y prime a to all times x is 0, and x is greater than or equal to 0. So this is your complementary slackness condition, these three together for the variables x, and these are the complementary slackness conditions for what we call the lambda, the Lagrange multipliers. The KKT conditions are necessary and sufficient conditions for an optimal. 2 implies that this part has to be equal to 0 as long as x is greater than 0, or x is 0 or both. 5 implies that this has to be multiplied by x, so this one here by y, so y is 0 or this part is 0 or both. And these are so it's really 2 and 5 that are your complementary slackness conditions. Dual, we have a greater than or equal to sign, and with the primal it's less than or equal to. Okay, sensitivity analysis in linear programming. The idea is to examine the range over which the optimal solution applies. Remember, we had a straight line constraint, and with a straight line constraint, if the objective function fell right on top of it, you could go from one point to the next and still have an optimal solution. So there are cases where you can make quite a few changes in the C vector, in one of the elements in the C vector, without changing the value of the objective function, even though the solution might be a little different. Or pardon me, you don't even want the solution to differ. So the idea is to examine the range over the coefficients in the objective function, the C vector, the values of constraints, so the right-hand side or B vector. So in other words, how much could you change the B vector in any given constraint set by before it changes the optimal solution, and finally changes in that technical coefficients or A matrix. Some extensions to the simplex algorithm or method. If the linear programming problem is in standard form with only less than or equal to constraints and B values that are all positive, then there's no problem with the simplex method achieving a solution. There's a problem if there are less than and equal to, greater than and equal to, and equal to constraints, and or some B values are negative. Then we need to use what's called the big M, or the phase 1, phase 2 method, and these involves, or the latter involves, artificial variables. And we'll just mention that briefly. These artificial variables are slack variables that are added if you have a less than or equal to constraint, but they're surplus variables that are subtracted if the constraint is a greater than or equal to constraint. So we subtract a surplus variable to ensure that that constraint is met. Artificial variables are added to each constraint that's not satisfied if the x's equal 0. So if the right-hand side of a less than or equal to constraint is negative, an artificial variable is added in addition to the slack variable on the left-hand side. If you have an equal constraint, an artificial variable is added, but you do not have any slack variables. And to a greater than or equal to constraint, an artificial variable is added since a surplus variable was subtracted. Why? Well, we need to ensure that a non-negative initial feasible basis exists. We can't have negative numbers in there because there are no negative numbers in these kind of economic problems. Negative numbers don't come in. All artificial variables under the big M method, all artificial variables need to be driven out of the solution before we get a true feasible basis. So the big M method does this by adding an arbitrarily large negative penalty on the artificial variables in the objective function. Recall that the coefficients on the slack and surplus variables are going to be 0. So here we introduce artificial variables, and to those variables we put a large penalty, so a negative value. So you can imagine if you're trying to maximize something and you have a variable, call it A for an artificial variable, if it's negative and it's a big negative, then the first thing that the algorithm tries to do is get rid of that big A. If the artificial variables cannot be driven from the solution, even if the penalty is set very large, then the problem is infeasible. And finally, the phase 1, phase 2 method is used by computer algorithms. Solvers automatically put in the slack, surplus, and artificial variables. In other cases, an interior point algorithm or mixed interior simplex method is employed. So it's not always that linear programming employs the simplex algorithm. Sometimes an interior interior point algorithm is used, but still the simplex algorithm is the best. Phase 1, we replace the objective function with the sum of artificial variables and minimize this sum. If the minimized objective is non-zero, the solution is infeasible. Phase 2, we use the basis found in phase 1 as the start of the simplex algorithm. So as you can see, there are all kinds of little fancy techniques that can be used to solve problems when you think there's no solution at all. But generally, if you structure a problem sufficiently, taking into account convexity and concavity of your function so that the constraints are convex and the objective is concave, then generally you do not have a problem. So it often revolves around whether or not you've specified your numerical linear programming problem appropriately. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.